Let me start immediately with introduction, and I hope by the end of the talk it will become clear what participants in our workshop are interested in. So first part of my outline is just light introduction. I borrowed quite heavily from brilliant lectures that Richard Hemming gave in 1993. If you've never seen them or read them, I strongly recommend. I'm going to start a bit philosophical. Okay, if you disagree, that's my personal opinion. Because we are wired biologically in a certain way, colors we cannot see, sounds we cannot hear, smells we cannot smell. Each time we face a limitation, usually we solve it with tools. And we don't just solve it, we exponentially amplify our limitations. When it comes to colors, we can see very faint light as well as the entire spectrum. When it comes to the sound, do more or less the same. And suspect device that allows you to smell looks something like this. Apparently, it's an actual device. I don't know how it works. But if our biological constraint limits us from seeing, hearing, and smelling, it's not entirely inconceivable that some of our biological constraints also limit us from thinking of the thoughts. Perhaps there are thoughts we cannot think. If you're not comfortable with simulation, that's okay. I can say it in a bit more cautious way. Maybe there are patterns we cannot detect. Or perhaps there are patterns we can detect, but we need exponentially long time to do so. Now, you may say it's hard to conceive the thoughts you cannot think. But I challenge you to imagine a color you cannot see before we understood electromagnetic radiation. Or for that matter, hear a sound you cannot hear. I still cannot imagine smells I cannot smell. But, to be more concrete, let me give you two examples of either thoughts we cannot think, or in the very least, patterns we take really long time to detect. One is AlphaGo. It defeats now all possible human opponents. For many years, it was true. Why does it do that? Well, one way to say is it thinks differently than human opponents. Perhaps, in the most generous case, we can say it thinks much faster. Human opponents just cannot keep up. So that's an example of a pattern that a tool can detect much faster than a human. Another example is a bit closer to science. It is a form of science, namely the prediction of the protein shape from the protein structure. In this case, the data that allowed us to do so has been around for at least a decade, maybe more. But we have failed to see it. The scientific community have failed to figure out correlations in the structure that can be used to predict the shape, relations between structure and the shape. And instead, what happened over the last few years, a tool was built that can detect the correlations and therefore predict shape from structure. We still do not know really how it works. We still do not understand the correlations, but it is quite interesting that it seems it was faster to build a tool that can see correlations we cannot see than to see the correlations. Unfortunately, you may argue that the problem of detecting protein shape from protein structure is not solved because we do not fully understand how AlphaFold works or what correlation it detects. As a result, we are not really confident in what it does. Or at least if you are very conservative, not really be confident in its predictions. Like many of you, I was brought up with the idea that, I guess was coined nicely by Feynman, that if I cannot create something, then I definitely don't understand it. Today, and AlphaFold is an example of this, there are systems we can create but do not understand. And it's not just we can create them, we understand if they're microscopic completely. We know everything about them there is to know. However, we cannot predict their behavior to any degree of certainty. Incidentally, Feynman was very clever. Existence of AI doesn't contradict logically what he says. Think a little bit about it. If you ever would like to use AI as a tool of science, probably we should understand how it works. And that's what our workshop is about. So in the rest of the talk, I'm going to try to articulate to you that just like physics, AI is an experimental science. There are there's plenty of experimental data, plenty of experiments in AI that require explanation. And I can't imagine a better community than theoretical physics to do so. To emphasize that AI is an experimental science, I'm going to structure my talk as follows. I'm going to go through experimental details of how large language models are trained. I'll outline 10 steps from data collection to some details of prompting them. And whenever appropriate, I will mention relevant theoretical work or theoretical puzzles. That's how the rest of the talk. During the talk, feel free to ask the questions. I may not know the answers to all of them. In that case, I'll call upon the audience to help me out. Disclaimers before I start speaking. One is I have never been part of an LLM team. Whatever I learned from papers or talking to people who are not under NDA, which means that some of the most modern LLMs may work differently from how I describe because they are under NDA. Some of the smaller models, released within a few months, are available, and I will mention them when possible. Okay. Before outlining the steps, let me spend an extra minute about where we are now. So when it comes to large language models, so here's a plot I just found on the internet. Was the size of the models measured in the number of parameters as a function of time over the last years. And you can see that there is a trend where the models keep growing in size. However, if you look maybe at the last year or so, the models are possibly no longer growing in size. And if I make it to the relevant parts of the talk, I'll explain what changed the trajectory, what empirical results changed the trajectory. One last thing is if you'd like to interact with these models, now there is a chatbot arena you can all participate in. You can just Google it. These are current results. There are 5 different language models in top 9. And I feel like this table says a lot, but perhaps I not spell out the obvious. Okay, so a lot of things out of this no spaces. The first step is to take each one of the symbols and convert it into an integer. Integers are called tokens. And after I convert the letters into the tokens, I also convert the tokens into vectors. It's called embedding. So E0, E1, E2 are vectors in some dimension whose some vector space whose dimension is chosen, and this choice also is a part of the design. There is no prescription how to choose it. And these vectors are given to the model when the training is done. Now, unfortunately, that's not where it ends, because it should be intuitively clear that letters is a little bit too much of a UV description of the text. I want to include a little bit more structure. The way it's done is by taking the combinations of tokens that frequently appear in the data set and giving them a new token. So one example that I'll give here is, imagine that AA in this Gedanken text appears very frequently, maybe almost as frequently as C. It makes sense to give AA an extra token. Now I enlarge the tokens from 3 to 4. And this new token I also embed with a new vector. During the process of training, these vectors are learned. Initially, they're random. To illustrate how it works, and to let me give you an example. Suppose I had this word, and it had ABC, AA. So it's an initial letter-wise tokenization to look like this. I just converted letters to symbols, letters to just using this rule. But if I include AA's next to token, the sequence got shorter. What I did is I enlarged my vocabulary by 1, but I saved 2 tokens. Tokenization is really a form of lossless compression. There are different ways of doing lossless compression. There are plenty of ways of doing tokenization. As you may guess, if you keep doing this, you have to find a compromise between the number of unique tokens and total size of the text of your data set as measured in tokens. If you just use letters, your data set is going to be huge. However, if you just use words, some of the tokens the model will see only once. The words are very rare. You have to find a compromise somewhere in between. And for example, GPT-3 approximately ended up having 0.7 words per token. So they say in the paper. This plot looks two-dimensional, but it's not really, because there are different ways to take the frequently occurring combinations of tokens and assign them new token. Each model uses their own. One of the most popular ones is called pair encoding, but there are many different ones. It's not clear which one to use. It's not clear how to find a compromise between vocabulary size and total number of tokens. Typical vocabulary size that's used nowadays, 10 to the 4, 10 to the 5. Just to make sure you don't get lost in the jargon, vocabulary size means number of unique tokens. So in this case, it was 4. In this case, it was 3. Once we represented the data, wait, feel free to interrupt me, because I'll just go through steps and stop it. Once you selected and chose how to represent the data, we need to choose the neural network model that is going to be trained on it. At the moment, community settled on a very particular type of architecture that's called decoder-oriented transformer, depicted on the left. I'm not going to explain what different parts of it do. I'm just going to say that this is where text comes in. It goes through a very special layer called masked multi-headed self-attention. Then it goes through some other layers. Then it comes out, it enters the same block. It enters a new block that looks exactly the same. The process repeated many times. The number of times it's repeated is somewhere close to 100 less. The number of blocks is called depth. The number of parameters within the block, roughly, is called width. Whenever you choose this block, you have to choose activation function. Activation function lives in this feed-forward part. Feed-forward part is what you see in every talk about neural networks, the picture where every neuron in the previous layer is connected to every neuron in the next layer. One of the choice there is to choose the activation function. The most popular is of today language model is called Swiglo. A version of it is on here. Finally, you have to select what's the length of the sequence that the model will see at a time, called context length. And for a while, it was around 1,000. The biggest one accomplished of today is 10 to the 5. In addition to making these choices, you also can do tricks that allow you to train faster or to do inference faster. Needless to say that there are no laws of nature that tells you what to choose here. All of this is found by trial and error. You could benefit from theoretical understanding. Are there any questions about it?
Between the different networks, the main differences would be here or in the tokenization or everything?
Between different language models?
Yeah, you showed like a bunch of them.
Yeah, so some of the difference will be in depth and width. There will be difference in tokenization. There will be difference in tricks they're using to make them work faster. Will also be slight difference in which data they chose. And I have 7 more steps. And in those 7 more steps, there will also be differences in every single one of them. Okay, so once we show, for that, if you're not interested in language, but if you want to solve a custom science problem like protein folding, you have to design a custom architecture, which is quite difficult if you don't understand the principles of architecture design. My understanding is this is a picture of AlphaFold 2. My understanding is this was found by trial and error. There's a horrendous block that's repeated 48 times. And we don't really know how it works. We don't understand the correlations between structure and shape. Once you figured out your data and architecture, you need to make another decision. You need to decide how much data to take from your data set and how many parameters include in your neural network. One way to explain this quantitatively, the trade-offs that you have to think about, is to make a plot where the vertical axis you take log of the amount of data, and horizontal axis take log of the number of parameters. you are never really constrained. You're almost not constrained by the amount of data, nor you are completely constrained by the number of parameters. The thing that does constrain you is cost, either measured in total number of floating point operations or in dollars, as you like. And the cost roughly equals to the product of the amount of data times number of parameters. What I'm going to do is I'm going to plot lines of the constant cost on this plot. And once you figured out your budget, you still need to decide at which point on this line you want to be, how many parameters to take, how many data points to take. There's a belief in the community based almost exclusively on empirics, I would say, that the optimal performance, or perhaps in more concretely, smallest loss, is achieved when there is a power law relation between number of data points and number of parameters. Namely, number of data points is some power of number of parameters. If I knew alpha, and if I believe that such optimum relation does exist, in the same plot I can draw another line where d equals alpha log n, and the intersection of this line with that line will tell me how much data to take and how many parameters to take.
How come it doesn't depend on the dimension of the inputs?
So there's proportionality sign. But what you think about is you can scale d, you can scale n, but that dimension, input dimension kept fixed.
Does the parameter scale with the dimension? Let's say I have images and I just keep.
So d, roughly speaking, is number of words. N is number of parameters in every layer. It depends on what you mean by dimension. There is
an image and I keep taking higher and higher resolution. If there is scaling involved for that.
higher and higher resolution in what sense?
So pixels increase, like dimension of the inputs are larger and larger.
Dimension of the input, okay. Then you will also increase number of parameters.
And is there a scaling involved between them?
I don't know. Anybody?
You mean, sorry, dimension of the inputs, you mean just the vocabulary dimension of the tokens? Or so in the original scaling laws paper, there are like various choices that are left out of here, like the width to depth aspect ratio and other various things. And they basically, you can think of it as just not change, like the power law for the alpha is like a universality class, and that everything else, like aspect ratio, other these things, like they can affect things, but they don't really change the power.
So that's the next slide. Oh.
Yeah. But that's almost every other design choice is likely not to affect the power.
Yes.
Somehow intuitively, I would also have thought that it's not a power law between the data and number of parameters, because if you have more data, then you start to generalize and actually need less parameters if you find generic patterns in that data. But is it true? Or?
Well, I mean, all I can tell you is what's known experimentally. And experimentally, it seems to be true that if you take more data, you need to take more parameters to do better. The real question is, for every data point, how many more parameters should you add? Differently, alpha is positive. I think the situation you're describing is alpha being negative.
Yeah.
Experimentally, alpha seems to be positive. Whatever theory work does exist also suggests that alpha is positive. The actual value of alpha is what we're going to discuss next.
Does it mean that you don't find some kind of unification theories in that data, but you really learn some small tricks to basically survive as in the training?
Okay, so let me tell you what's known about this relation empirically. The initial paper is from OpenAI a couple of years ago. They measured loss, how test loss scales with number of parameters at fixed amount of data, and how it scales with amount of data at fixed number of parameters. With those two measurements, you can determine the value of alpha, and they found that it's less than 1, 70. What it tells you is that for you increase the data set 10 times, and to increase number of parameters is 10 to the power 1 divided by alpha. So, or if you increase data by some amount, number of parameters has to be increased by more. Okay? This belief led to very rapid increase in the model size, which is what we saw on that plot I showed a while ago. A couple of years later, that was revised by DeepMind. Incidentally, as Shona mentioned, this is not the only plot from the paper. It contains a good number of plots. And in particular, they checked that depending on various choices, this exponent doesn't seem to change. Including the aspect ratio as shown in this plot. In this plot, fixed number of parameters, the number of layers has changed, and they don't see any gain in depth, any increase in performance with depth.
So the exponent must depend on something like the task, or is it just universal?
Oh, let's continue. A couple of years later, this was revised. It's by DeepMind. They did similar set of experiments on the same architecture, and they found that exponent is 1. 0.74, which means that amount of data and number of parameters have to scale proportion. You may ask, what did they do differently? They used roughly the same data set, but for things they used learning rate schedule that's different from this paper. This paper investigated the dependence of alpha on learning rate schedule, and they didn't find the dependence. So as far as I can tell, the value of alpha, what it depends on and what it doesn't depend on is completely open question. Most likely, it weakly depends on everything. Let me mention here that technical report on Palm 2, the newest Google large language model, suggests that this scaling likely still holds. The model Llama that I mentioned before from Meta, their experience suggests that alpha is bigger than 1. They kept number of parameters roughly the same as models cited in this paper. Number of tokens is substantially larger. So value of alpha probably depends on a lot of things, including data, including how you train, probably on the quality of data, might be on architecture. As far as I can tell, it's completely open, empirically and theoretically. This is the place where I can mention theory, because yes.
So does the same scaling relation also hold for like image recognition tasks? Or have people?
There's a similar scaling relation, but I don't remember exponent on top of my head, and image tasks seem to benefit less from the new data. So at some point you reach some amount of data. After that, increasing data doesn't seem to benefit you. So do you know the exponent on top of you?
It's much sharper with the language, so you throttle much more.
Yeah, do you remember the exponent?
Or
Visual.
Alpha?
There is something similar, but you benefit less from more data.
Can you go back a slide? It's just a like fun aside. So
Yeah.
you see the shape matter plot with the aspect ratio?
Yeah.
You might notice that one layer is actually pretty off trend from the rest of them.
Yeah.
We actually have a pretty good theoretical understanding that one layer transformers are actually in a different universality class than like multiple layers.
Okay.
With like the induction heads and formation of like novel circuits that only exist in like multiple deep layers. And it's just anyway, it's just a fun plot because when they made that, they had no idea why one layer was going to be off trend, but there's like a good theory explanation for it.
Yeah. Okay, so there is some theory work on scaling. I summarized the subset of it here, including the authors, set of them here now, subset of them here will be next week if you're interested. Let me just briefly describe the takeaways and how this theory of work is done. Experts, feel free to correct me if I say something wrong. The starting point in I think in all the works is a linear model, meaning that you assume that your neural network depends on your parameters in a linear fashion like this. These functions phi called feature maps, and they can be chosen randomly or they can be chosen based on the architecture. But either way, they're fixed. When you do this theory, they are not learned. Whereas in many realistic setup, these functions are learned. Then MSE loss is calculated for this model and for a particular chosen data set. And it's calculated or estimated in the end of training. When you do this, you find that there are regimes. In one of the regimes, the test loss is a power law in the amount of data and in the number of parameters. And the exponents are some non-universal numbers determined by the data. top of my head, I actually don't know a single theory paper where theta and zeta prime are different. I think all theory papers find that they're the same. In a different regime, this law scales also the power law with data and number of parameters, but the scaling exponent is 1 and doesn't depend on data in this universe. A more general scaling relation is written here, and when either n is much bigger than d or d much bigger than n, it gives you this behavior. Let me just briefly mention that this work does not include feature learning, which is the reason why deep learning works in the first place. It also calculates MSE loss in the end of training, which means that they break the relation between the cost and number of data points and number of parameters. Being in the end of training means that you train for infinite time, which means you are in the infinite compute regime. Whereas in any real experiment, ND and cost are tied. You train for finite number of steps.
Yes. Could you define what test loss is?
Test loss is the loss calculated in the data you have not seen.
For a non-expert, what does that mean?
Sure. I'll write it here. In the simplest example, this is the neural network. This is the rect label for the data point. And let's say it's squared divided by d. You're training the simplest possible scenario for minimizing this expression over the parameters. The x's and y's you're using in this minimization process is called train set, and x's and y's that were not used in the minimization process are called test. The loss evaluated on test set is called test loss. Okay.
So
Yes.
if psi is psi prime, and I fix the cost, right, and times these constant, shouldn't I get alpha equals 1?
Exactly. So this is an interesting point. This alpha in the linear model, alpha is 1.
Oh, this relationship of fixed size is for the linear model. No.
So this formula was found empirically. This paper, just by fitting things. The paper by Dan and his collaborators derived this. They find that zeta prime equals zeta, and zeta is determined by the data, by the correlation, by the spectrum of the correlation matrix of the data. Okay. Once you decide on the scale, you need to figure out how you're going to train the model. And this is a real jungle. It's purely empirics driven. Amount of understanding is precious. So let me just emphasize what kind of choices you have to make, but the recipes are all empirical. So you have to choose the optimization method in the first place, which means you have to choose an algorithm that minimizes this over the parameters. The most common choice is ADAM-W, particular type of further method that calculates gradients and moves towards the minimum in a particular way, which I don't want to go into details about. Once you chose the optimization algorithm, you have to specify further details. One of the details is the learning rate. And learning rate is the size of the step you make each time you are moving towards the minimum of the loss. However, our learning rate is a function of training time. And it's not just some function, it's picked from a large collections of functions. What happens usually in the beginning of training, the learning rate is increased from some value to some other value linearly. There are other ways of doing it. This process is called warm-up. And once it's reached some predetermined value, it's decayed to some small value that's also predetermined. The curve that it follows when it decays is not unique. There's no of nature that says it has to be cosine or 1 over time or 1 over square root of time or 1 over time squared. There's a very large number of choices, but is this how steep this cosine decay is the difference between these two papers, which in the end gave the different exponent. Next, Adam also requires you to specify something that's called momentum that roughly speaking gives inertia to where you are on the lost landscape. If lost landscape becomes flat, you're moving due to inertia. You don't get stuck in flat regions because of momentum. You have to specify how much data that you use to calculate a single step of gradient. I mentioned before, I showed you a table, the total data set is very large. You cannot calculate loss on all of it. You split it into pieces, calculate the gradient on each piece, make a step. And once again, there is no obvious prescription how to do this. This amount of data you use per step is called batch size. And in large language models nowadays is roughly 10 to the 6 tokens, but batch size can in principle, just like learning rate, change in time. And some papers experiment with this, others fix it once and for all.
Is it possible to choose the learning rate adaptively based on how the loss function is evolving?
Many adaptive versions as well, but empirically, this one seems to work the best. Yes, you can normalize it by instantaneous norms of the weights. In fact, you can do is you can learn and optimize it. And that will try to adapt to the landscape. But that seems to be the safest route. You want to minimize the risk of you train large language. You also have to choose something called regularization. Just particular ways you can do it. I don't want to go into detail. Sometimes your gradient ends up being accidentally too large. If it's too large, you want to cut off, and that's cutoff is called gradient clipping, which also is a parameter. What's very disturbing is that all of these choices are non-linearly coupled to each other, to your choice of data and to your choice of architecture. It's very difficult to say to make an experiment where you keep everything fixed and then change just one thing, because everything interacts with everything. Okay, once you decide how you train the model, you have to decide what happens at time equals 0, initialization. Parameters, you have a lot of them, so it's unlikely that you will go parameters one by one and initialize them by hand. Usually done is they're sampled from some random distribution. Most often it's Gaussian uniform. There are some variations on this. And you choose the, say, Gaussian distribution, each group of parameters, you have to choose the variance of the distribution. And you have to be careful when you choose the variance. If you choose the variance poorly, then at initialization, your gradients, when you try to make the first step in the optimization process, end up being either very small or very large. And either you will not train at all for a while, or you will immediately diverge. One of the reasons Adam is good is it allows you to not really think too hard about it, because Adam, for perhaps not fully understood reasons, very resilient to thoughtless initialization. Whereas SGD, which is a classic gradient descent that you probably learned in college about, calculates derivative and steps towards that direction, very sensitive. There are some other tricks that allow you to reduce sensitivity to initialization. In addition to practical aspects of it, I'd like to emphasize that non-systematic initialization makes it nearly impossible to compare models at different scales. Because if you initialize models the same way, irrespective of their size and of their architecture, then it's very difficult to make apples to apples experiments.
Quick question.
Yes.
Sure. So do they have a similar statement how the train error and the test error deviate in these different sort of size?
What plot over where? Sorry.
The argument there is that the largest batch is going to be the fastest, right? Is that what
You mean this plot?
Yeah.
So the point of this plot, I decided not to wait. I decided to put it, but not talk about it, is that the benefit of increasing the batch size eventually saturates. See, there are a bunch of curves that are on top of each other, and they differ by the batch size. Okay, what you would like to do is you would like to take the smallest batch size that's close to this set of curves. Okay.
Is there a large deviation between train and test errors, though, if you take the large batch size?
There is no, so it's language models. There is no really train error. So you see the entire data set once, you just calculate you can define train error on data you have seen once, but people don't really plot it. Yes.
Is there any understanding of the scale at which it's saturating that?
Well, there is an empirical paper that from which I actually took the plot. You have to measure the noise and some noise scale. Increasing the batch size no longer yields the same benefits in decrease of the loss.
And the noise here, is it from SGE?
Batch, so when you change batch size, there is noise. If your batch is small, your gradient is very random because the loss, very poor approximation to the true loss. Point of this plot is that naively you may say you want to go to as large batch size as possible, but in practice there is some sweet spot. If they give you prescription how to determine it, do this, you measure the noise. Okay, so initialization is the place where there is a lot of theory has been done. I summarize some of it here, and let me just explain very roughly how this theory works. So if you want to ensure that your model doesn't blow up or gradients don't vanish at initialization, you would like to impose two constraints. Constraints are quite simple. The first constraint is that if you send some vector to the network, you want to make sure that the norm of this vector fluctuates a little bit, but doesn't decay or blow up exponentially in depth. Okay, so that if vector was order 1 here, it would be nice if it remains order 1 everywhere. Of course, one way to achieve this is to renormalize vector after each layer. Actually, that's what's commonly done. This operation is called layer norm, and it is indeed part of the transform. But you don't have to. If you choose initialization properly, it will propagate and remain order 1, or in the very least, its norm will change algebraically with that. And this is a constraint on sigma, the variance of weights and biases. Another constraint is just as simple. It's propagation in the opposite direction. You calculated the gradient. You want to make sure that the gradient for each layer is also roughly the same order of magnitude. And that's another constraint on sigma. Unfortunately, for gradient, there is no layer norm. You cannot just put some other layer on the other side, hope that the gradient will get normalized. Controlling the gradient is harder. And that's what residual connections are for. They're also part of the transformer. So if you impose these two constraints, you end up with a constraint on the variance of weights and biases. However, as I mentioned before, it may no longer be as important because Adam is not sensitive and Adam is. Here there is also much more work that can be done. For example, there is more statistics than just norms of gradients and activations. There are point correlations, there is Hessian. Some of these things may give you more refined prescription how to initialize. It's not super clear why Adam is very insensitive. Perhaps Adam is sensitive to some other things, not the constraints that are followed by fixing the norms. Of course, it would be nice, as somebody just mentioned, to be able to adjust hyperparameters during the training on the fly, but we really have to understand well what happens during the training. And we are nowhere near here. Finally, it would be nice to know how to initialize architecture you have never seen before without doing many experiments. Okay. in the interest of time, maybe I will skip these two theoretical papers on initialization. I apologize to the authors. Let me go to the actual training. At some point, you have set everything up, and it feels like you just push a button and it trains, and you take a 1 month long vacation. But unfortunately, it doesn't seem to work this way. So if you open this GPT-3 paper, these are the curves that they give you, and it looks magnificent, just slowly decreasing with weeks and months of training. What happens in practice is that you have to babysit it for two reasons. One reason is that periodically loss blows up for no apparent reason and training stops. The fact is not understood. And the empirical solution to this is to restore model to the closest checkpoint, remove the data that led to the explosion, and continue training. It was actually done. Another issue that happens.
Sorry, what you just said, so it's just like numerical precision errors, because you said you return to the exact same point, you play things again and you get a different result.
You remove the data that leads to the explosion. There are various ablation experiments. For example, you can say, oh, you have just like really crappy data at this point. Some experiments would rewind model a bit back, take the data that's supposed to lead to explosion and give it earlier, and it doesn't. It's not really clear. What are the reasons? Precision might be involved, yes.
Sorry, I thought all the data was inserted at the beginning of the thing. That obviously isn't.
You have, in language, you have just a gigantic pool of data. And you just reach to the pool, give the model a batch. Reach to the pool, give the model a batch. You can rewind model back and say, well, maybe these two batches weren't good. Well, let me not give the model. Let me reach for the new batch and model. Another thing that happens when you train on thousands of GPUs is that sometimes they break. And when they break, in most cases, you have to restart the training manually. So there is the model, as I mentioned, by Mosaic MPT 7B. They somehow figured out automatic way of doing it. Don't know if all companies now know how to do this or not. But they also claim that they never experience loss spikes because they use this other optimizer. Judge may or may not be true. Okay, so that's that for the training. And once we have trained the model, you may want to specialize it to some particular task. To do this, you take a smaller but very high quality data set that maybe you paid somebody to make, and you train the model on the data set. Everything that I said about the training that does not pertain to initialization and choosing the architecture, through here. You train on this smaller data set, you still have to choose optimizer and page size and all of this hyperparameter. An example of how this works and what it is to is Minerva from Google. Is a large language model that's based on their Palm 1, and then fine-tuned on highly curated data set that contains text math problems. And this data set is about 120 size. The data set that Palm was pre-trained on. But if you go to the paper where they summarize the performance of the model, it's really good in solving text-based math problems. Fine-tuning does work. However, I think we only have a verbal explanation why fine-tuning works. Model learned a lot from looking at random text. And now that we give it a highly curated text, it's smart enough to learn quickly. But I'm not sure there is a better explanation.
You know why they need to give it again natural language?
Oh, they mentioned briefly in passing that we also throw a little bit of the language. That's somebody who knows. Okay. Once all of the training is done, there's another kind of dynamics that's quite interesting for future learning. So once the language model is trained, you can ask it a question in, roughly speaking, two different ways. Either you can directly ask it a question. Here is example to translate from English to French. Or you can ask it a question, give it a few examples of the correct answer, and then demand the answer to the question you're interested in. And this improves performance. Model learns on the fly without updating weights at any point.
From that sequence, right?
So I think this is not particularly good example. I took it from there, from the paper. They have a bit more artificial examples where it actually works. For example, you can take an English word and shuffle the letters a little bit and ask it to unshuffle, or insert symbols that don't belong and ask it to remove. And then giving a few examples makes sense. That's a bit stupid, I agree. Yes.
For the future one, is the task description how important necessary is it?
This plot. Okay, let me say what I was going to say without jumping to the end of the sentence. But the short answer is yes. The more you tell it, the better it does. So here are the plots from OpenAI. It's from the GPT-3 paper where they see the effect of the few shot learning versus zero shot learning on the performance. And the bigger the model is, this of 2020, the more it benefits from having a few examples of the task it's trying to solve. So you see here, it would be normal prompt, and here is a few shot. And on the vertical axis is the accuracy. This is not a particular task. This is aggregate of 40 different tasks. On average, it seems to do better with prompts. Here is a particular task they considered. I think that's the task of taking word, introducing some weird symbols into it, and asking model to remove the symbols. So here, you can give a lot of examples in the future learning. And again, the bigger the model is, the more it benefits from giving examples. So on the x-axis at 0, just ask it directly to do the task. It's confused. You give it like 10, maybe close to 100 examples, accuracy goes from close to random guessing to 60%. So giving it examples works, but you don't update the weights. It does some other type of learning, some other type of dynamics. You should have basically no grasp on at this point. Somebody asked the question, so natural language prompt versus no prompt means that you literally ask it in English what you wanted to do, and no prompt, you just give it examples. Ask it to, and it also makes a difference.
Is there any analog of few-shot learning for not language models? Like, what would be the analog for like an image classification task?
I don't know.
Okay, so this is only a thing that belongs to language models and
Maybe to any sequential data.
If you have like object recognition and you tell it about some of the objects in the image and tell it to find all, I don't know, all the other people, right? You circle around your people.
Oh, actually, yeah. So now you're speaking about it. There is this very recent segmentation model from Meta, where you ask it to find objects. You can pinpoint particular object type of object you're looking for, and it can find similar objects in either the same image or different set of images.
It's also a property that really only happens at large scale. So you could just see, right? Like the tiny models don't benefit nearly as much. And like almost every model that's not a large language model is incredibly tiny.
What's the algorithm for that image segmentation?
It's a neural network structure. I'm not familiar. It's called SAM if you'd like to Google.
Yes, okay. Segment anything model.
Yeah.
That's the name of it.
There's no deterministic algorithm. It was learned. There is one very interesting paper on the theory of future learning from Google from about a year ago. In that case, the task they were trying to learn is not language, but they learned how to fit linear functions, trained a linear self-attention, do this with square laws and so forth. And when the model is exposed to sufficiently many linear functions and explained how to fit them, it discovers, perhaps maybe a bit too basically discovers how to do gradient descent. It imagines some emergent objective function, and given a context, minimizes it. It has one layer, it does one step of gradient descent on this emergent objective function it has imagined, and if it's many layers, it has L steps of gradient descent. What's remarkable about this paper is they took linear self-attention, just by hand wrote the weights that do that, and then trained the model and saw that the weights the model finds are quite similar. Okay. Well, how much time do I have? A couple of minutes. Okay, maybe I'll even make it on time. Another way another variation on this few-shot learning is called chain of thought prompting, which, again, I don't know how naive description this is, but roughly you can think of it as model learning the algorithm context or in a few shots. You can give it not just an example of question and answer, you can give it an example of question, reasoning that leads to the answer, and then the answer. And then it does much better than just knowing question and answer. In fact, Minerva was using in a thought prompting. I do not know how popular, whether all language models trained on to solve some math tasks are using it, probably. But that means is that giving exposed to a few examples of reasoning, the model can very quickly pick up on, again, without updating the weight. Finally, there's a reasonably controversial topic that I'll just mention that it exists. Again, there is a collection of papers talking about it, which is discontinuous improvements with scale. Here's a few examples of tasks. I took this from one of the papers from Google. So here, what you see is some tasks. Performance of the model as a function of scale. Scale here is measured in flops, but there are similar pictures when scale is measured in the number of parameters. And as you increase number of flops, performance on this set of tasks doesn't change much. This dashed line is a random guessing, but eventually, when you reach some critical scale, it increases very, very rapidly. There is no known way to predict when this happens, and there is no clear picture of why and how this happens. There is also a bit of a debate whether this is a true effect or it depends on how you measure performance. But I think as to the physics community, that must sound quite familiar. When you change a parameter, something at some point dramatically changes. Yes.
So since I see here model arithmetic as an example, and this kind of vaguely is reminiscent of grokking, which I heard about, is this related or do you think? Okay.
We're on the same wave. Okay. So the most trivial example that I'm familiar with is grokking. However, there's a slight difference is that in grokking, you don't change the model scale yet to this effect. You train it for longer. If you measure scale in the number of flops, it checks out. If you measure scale in the number of parameters, it doesn't. But indeed, there is an effect, as has been studied in this set of papers, where you give the model a data set like this, where n and m are integers, and you ask it to predict the third symbol, which was sum of the integers mod p is some number that will specify the data set. You train the model very quickly, achieves 100% accuracy on the data it has seen, which is not surprising. There are a lot of parameters, you can overfit anything. But then as you keep training, suddenly and quickly, the test accuracy goes from 0 to 100% as well. So that is indeed a little bit reminiscent of this, but I was debating whether I should trust this to effects or not. I decided to mention it, but it's not clear whether this and that are the same thing, nor is it 100% clear whether this even exists. Incidentally, when you measure loss rather than accuracy, there is no abrupt transition. Everything is smooth. Since I'm almost out of time, go to conclusion. Just trying to articulate to you most of all that AI, genetic physics, is experimental science, and we do not think it will benefit directly from any formula we know in physics, from any model that we are commonly working with in physics. That does benefit from is the style of research we're doing, which is we operate using empirically motivated models and approximations over mathematical rigor. If the model agrees with experiment, is for us is better evidence that it's correct, and it's constructed in a mathematical rigorous way. And I hope I articulated to you that numerous experiments and effects that require understanding. This kind of research on understanding is unavoidable if AI is ever to be used as a tool in scientific research on par with quantitative theory and numerical simulations, and not as some second-class citizen. So this research, it's not avoidable. This has to be done in scientific research. And I cannot imagine a better one, theoretical physics. I will leave you with Law from ChatGPT that also tries to encourage you to switch your field. And that's that.
Is there some specific post-training that teaches ChatGPT to the question and answer format so that it knows?
I think we have a better person in the audience to answer it.
So what was discussed here was fine tuning in a sort of unstructured supervised learning way. So specifically in the slides, when I talked about Minerva and math fine tuning, you had this big corpus initially of language data. It was just kind of a random mix of stuff. And then you have this loss function, which is predict the next token. And then they curate the data, and then they still do predict the next token on a static corpus of like high quality data. What gets ChatGPT, GPT-4, Claude, and all these sort of more recent models to the point where they are is actually a slightly different fine tuning method, which uses reinforcement learning rather than supervised learning. So the model is actually training on its own samples in a loop where it produces some text, and we have some way of grading, is this a good answer, is this a bad answer? And we basically say, go for the maximum reward that like is the best answers according to some metric of best, and it's kind of complicated to spell out how to, that's a learned function. And effectively, some of what that does is it's a bit higher quality and a bit more reliable than in some cases. It's a bit harder to implement than the sort of traditional fine tuning. It's a completely different objective function. And it often has the effect of taking like what we talked about as like prompting, few shot. It often takes the effect of like what you would think of as like a 5-shot prompt and makes it just work out of the box with makes it work 0 shot. So like that's basically what they do for the question answering format stuff.
So to summarize, it's some human intervention in the post-training that teaches it not to behave in a Socratic fashion and answer a question with a question.
I guess
that would get a low score from a human supervisor.
Exactly, yeah. And in fact, we need to like train another model to act as the in-loop surrogate so that like, you know, you collect data in some manner, like what's better and worse. And then use another neural network to predict what that like data label is, which is effectively could be just what a human would approve of in some manner. And then that neural network is what you're optimizing against in the reinforcement learning. Yeah.
How many of these questions would you consider sufficient to answer before you would trust these tools to be used in a scientific context?
Me personally.
Sure, you know, from your biased opinion, because you're standing up there. Like, you know, because presumably it would take many decades to answer all these questions.
Once I trust it as much as any one of my colleagues, then.
Well, so let me give you an example. So I don't know how all the guts of Mathematica works.
Hmm?
Presumably there could be some bugs or typos deep inside Mathematica, and in fact, I'm sure there are. But I guess I trust that well enough to use it in results and papers and stuff.
Well, there is a group of people, mathematics is deterministic. As I can tell, there's a group of people that know how it works.
Sure.
Also don't know how a car works or a plane works. Still, drive one and times fly. The problem here is I'm not aware of a single human or collective of humans who know how it works. It's the fundamental difference. How many? I cannot give you like 17 questions or so, but I think eventually as a community we will equilibrate to having faith in it. It's just like with quantum mechanics, we'll get used to it. None of these problems will get solved. Theoretical possibility.
You didn't use the word physics-informed neural networks. How does that fit into this, or does it?
Also, I only talked about language models. If you are trying to, make a model that predicts some output of a physics experiment, you can constrain it to satisfy, let's say, to have a symmetry of the problem. Or maybe if you're studying quantum mechanics with fermions, we want to make sure that model knows about antisymmetry of the Fermi wave function. That would be physics examples of physics. Language, I don't think there are a priori that many rules. We want to have the model that is as unconstrained as possible. When it comes to physics informed, I don't know too much about it, but what I did see in the papers is that it seems that models can train better if you don't enforce the physics constraints, but you maybe just penalize a little bit. So the model deviates from the physics constraint.
So if you forecast to the future, everybody having their chat buddy or whatever, to solve physics problems, I would have expected that having a lot of informed prior information would be great.
So that maybe was a belief a couple of years ago. My understanding that now is the solution would look like you take one of these language models, maybe even better one that will come in a couple of years, 10,000 of physicists, and let them interact with the model. Eventually, it will be as good as the 10,000 physicists. Would that work this way?
I think another thing too is that like even this sort of unstructured approach is not strictly speaking limited to language. DeepMind has an old model at this point called Gato, which is effectively take the language modeling approach to everything: audio, video, images, robotics, trajectories on basically all data, like predict the next token, where token is not just like a word, but is like a frame of the video fed in through some embedding, whatever, and just throw that unstructured approach, big transformer, let it go on everything. And it basically works pretty well at predicting. If you throw a ball in the air in a video, it's going to learn that it obeys kinematic equations roughly. I mean, it's going to have some nice prediction because it can predict the next frame of the video, the ball moving, for example. It can move the robot arm around, and that requires some knowledge of physics because it has to, again, deal with Newtonian constraints on its kinematics and stuff. So
if the unstructured thing works, wouldn't it be good at some point in the learning to inject the kind of formulations that you get, which are like pins?
I mean, it's possible, but it seems that like as long as it just learning, I mean, it might be just like a trade-off of like maybe there's some clever scheme that allows you to save a bit on compute in order to accomplish the same thing, which seems like imposing the constraint means you get the same quality product for like, a few like millions of dollars cheaper or something like that. But that might take a bunch of humans to like figure out how to do it, and there's no guarantee that it'll work. Whereas if you just pour in all the data, it'll eventually just sort of sort itself out.
Well, I do like the concept of utility for humans in this process.
Yeah. Unfortunately, we're slow in comparison to
No.
Has this research given you anybody insight on how like a child learns how to a language, for instance?
I have no idea. It's a question. Yeah.
The theory of the brain. I think.
Anybody know? Did you learn more about children by studying a language model?
There were some like fun experiments I did with like small models versus big models around like, I think object permanence or something, where it was like you have this like text prompt experiment where you say, Alice goes in the room and like there's like somebody, she puts a ball in this location, And then, she leaves, Bob comes in, moves the ball, then he leaves, and then Alice comes back, and then you ask, like, where does Alice think the ball is? And because she didn't see Bob move it, you need some theory of mind to predict that Alex will be confused by the sudden displacement. And a language model that's really tiny will be like, we'll just point out the most recent location, or it will just be completely incoherent if it's like really tiny. Whereas like bigger models will be like, Alice didn't see the ball move, so therefore, she thinks it's in this place, but she'll be incorrect. And there was a jump in models being able to do that. So I don't know, this is kind of like a fun, I think that's like a classic theory of mind child psychology experiment that like some scale models don't get it, and then bigger ones do.
Yeah. How hard is it?
There was a question, then I'll get. Yeah.
So the discontinuous improvement before the dropping one, does that result depend on initialization distributions and stuff? Or
Can you say it again? Initialization what?
initialization of parameters and stuff like that, does that change the point at which that improvement happens, or is
The way these sort of experiments are done is they have a prescription of initialized parameters. I don't think they are willing to touch it. So, particularly for the biggest model, you just get one run. Don't want to touch.
Related to some of the earlier questions, how hard is it to incorporate factual correctness into the outcome of some of these things? Right? That's what's really missing right now. They can make sort of textual sense, but very badly.
The understanding is that you get it to interact with humans, get more feedback, it will get better. In some cases, questions you can ask don't necessarily have a right or wrong answer. Majority of things, humans don't have the right or wrong answer, so it's probably a very specific application. If you ask them, if you ask ChatGPT, GPT-4 version, actual questions, it often does it really well. Maybe also you can want to give it tools to search the internet and judge yourself what the answer is.
Silly question. Early on, you showed these ELOs of each of the large language models. And you know some about how those were determined? Because if you play using GPT-4, after about 10 moves, it starts making illegal moves. So you can't play a whole game.
Those are not chess elos.
Sorry.
Those are basically, they have a chatbot. The chatbot arena is you pair up two chatbots, but you have completion A, completion B, and a human says, oh, I like A better than B. And then that counts as a win for the model that produced A over B. And then you calculate the normal chess ELO formula, but on a different task.
Thank you very much. Good. So it is fully human.
Yeah, that is a human evaluated. You can do proxies with models that like sometimes people do for quick experiments, but yeah, I think this site is like some human, driven website.
A bunch of human anonymous people.